Radiofrequency, or RF voltage, is a high-frequency voltage used in communication systems such as radio and television broadcasting. Unlike low-frequency alternating current voltage, RF voltage behaves differently in materials. While insulation can prevent electric shocks from low-frequency alternating current voltage, it is often ineffective against RF voltage. This is because RF voltage can penetrate non-metallic materials, even insulators like rubber and plastic. In the situation of someone experiencing a shock from touching a bare RF wire, penetration through insulation is a key factor. The RF voltage in the wire can be high enough to penetrate the thin insulation typically used on RF cables. Secondly, capacitive coupling can occur. Even without direct contact, a person's body can act as a capacitor and couple with the RF wire, allowing current to flow through them. The National Electrical Code, or NEC, does not have specific requirements for RF wiring. However, it does require that all electrical conductors be adequately protected against physical damage and insulation failure. In practice, RF cables are typically run in conduit or other protective enclosures to minimize the risk of shock. To prevent RF shocks, several measures should be taken. Firstly, use RF cables with adequate insulation and shielding. This helps to contain the RF energy and reduce the risk of penetration. Secondly, run RF cables in conduit or other enclosures to block RF radiation. This provides an additional layer of protection and prevents accidental contact. Thirdly, post signs near RF equipment to warn of potential shocks. This alerts personnel to the potential hazards and encourages them to take necessary precautions. Fourthly, train maintenance personnel about the hazards of RF voltage and proper safety procedures. This ensures that they are aware of the risks and know how to work safely around RF equipment. RF voltage can penetrate insulation and cause shocks even with indirect contact. The NEC does not specifically address RF wiring but requires adequate protection for electrical conductors. Proper insulation, protective enclosures, warning signage, and training are essential to minimize the risk of RF shocks. When considering electrical safety in installations involving radio frequency equipment, several factors come into play. The unique characteristics of RF energy, its behavior, and the applicable safety standards must be understood. The National Electrical Code, while not explicitly detailing RF wiring, provides a foundation for safe electrical practices that can be adapted to RF systems. Firstly, RF energy is characterized by its high frequency. Unlike alternating current at 60 Hz, RF operates in the kHz, MHz, or GHz range. This high frequency gives RF energy the ability to induce current in nearby conductors through electromagnetic fields, a phenomenon known as capacitive or inductive coupling. Secondly, the behavior of RF energy differs significantly from low-frequency alternating current. It tends to travel along the surface of conductors, known as the skin effect, and can radiate into free space if not properly contained. This radiation poses a risk of unintended exposure and interference with other electronic devices. Thirdly, standard insulation materials like rubber and plastic, which are effective at blocking low-frequency alternating current, can be penetrated by RF energy. This is because the high-frequency fields can induce current in the insulation itself, leading to dielectric heating and eventual breakdown. Fourthly, grounding plays a crucial role in RF safety. A proper grounding system provides a low-impedance path for RF currents, preventing them from building up on equipment surfaces and reducing the risk of shock. The ground system should be designed to minimize ground loops and ensure equipotential bonding. Fifthly, shielding is another essential technique for containing RF energy. Shielded cables, enclosures, and connectors prevent RF radiation from escaping and protect personnel and equipment from exposure. The effectiveness of shielding depends on the material, thickness, and construction of the shield. Sixthly, regarding the NEC, while specific articles addressing RF wiring are absent, several general requirements are applicable. Article 110.3. The examination, identification, installation, and use of equipment mandates that all equipment be installed and used in accordance with its listing and labeling. This includes RF equipment and associated wiring. Seventhly, Article 250, Grounding and Bonding, provides comprehensive requirements for grounding electrical systems and equipment. These requirements are critical for RF safety, as a well-designed grounding system minimizes the risk of shock and equipment damage. Eighthly, Article 300, Wiring Methods, specifies general requirements for wiring installations, including protection against physical damage and installation failure. These requirements apply to RF cables as well, ensuring they are adequately protected. Ninthly, Article 400, Flexible cords and cables, covers the use of flexible cords and cables in electrical systems. While not specifically addressing RF cables, the requirements for ampacity, overcurrent protection, and proper use are applicable. Tenthly, Article 600, Electric Signs and Outline Lighting, provides requirements for high-voltage systems, some of which may be relevant to RF installations, especially those involving high-power amplifiers or transmitters. 11thly, regarding practical safety measures, firstly, use appropriate RF connectors and cables. Ensure that all connectors are properly installed and tightened to maintain shielding effectiveness. Secondly, route RF cables away from personnel and other sensitive equipment. This minimizes the risk of exposure and interference. Thirdly, use shielded enclosures for RF equipment, especially high-power amplifiers and transmitters. This prevents RF radiation from escaping and protects personnel and equipment. Fourthly, implement interlock systems on equipment doors and access panels. This ensures that power is automatically shut off when the enclosure is opened, preventing accidental contact with live RF circuits. Fifthly, provide clear warning signs and labels indicating the presence of RF energy and the potential hazards. This alerts personnel to the risks and encourages them to take necessary precautions. Sixthly, regularly inspect RF equipment and wiring for damage and wear. Replace any damaged or worn components promptly to maintain safety and performance. Seventhly, conduct RF site surveys to measure the levels of RF radiation in the environment. This helps to identify potential hazards and ensure compliance with safety standards. Eighthly, provide training to personnel working with or near RF equipment. This training should cover the hazards of RF energy, proper safety procedures, and the use of personal protective equipment. Ninthly, use personal protective equipment such as RF safety glasses and gloves when working with high-power RF equipment. This provides additional protection against exposure. Tenthly, consider using RF-absorbing materials in areas where RF radiation is a concern. These materials can help to reduce the levels of RF energy and minimize the risk of exposure. In conclusion, RF voltage presents unique challenges compared to traditional alternating current voltage. The ability of RF energy to penetrate insulation, its propensity to radiate, and the potential for capacitive coupling necessitate careful consideration of safety measures. By implementing proper grounding, shielding, and interlock systems, providing adequate training and warning signage, and adhering to the applicable requirements of the NEC, the risk of RF shocks and other hazards can be minimized, ensuring a safe working environment. Remember that the NEC, specifically the 2008 edition, serves as a guideline for safe electrical practices, and local regulations may impose additional requirements.